All right, everyone, we're going to start lesson 5, polynomial functions and complex zeros. Just so you know, this lesson will be broken down into 2 parts, so we will be doing the first half today. We're going to talk about zeros of polynomial functions. Remember, zeros are when a function crosses the x-axis. So that input value doesn't matter. The input value is going to be the answer here, but the zeros are when y, or the output, is at 0. That's why we call them zeros. It's those crossing points. So, if you have these functions, they will be written as factors often, like x minus 2, in which case the 0 is when x is equal to positive 2, right? You set these equal to 0 so that your output is 0. You find out that the input needs to be 2 in order to make the output 0 crossing the axis. Thing is, a lot of the functions we've done have had just one factor that matched. Now we're going to talk about repeated zeros. We call that multiplicity. That happens when a factor like x minus a is repeated more than once. Typically, a graph passes through the zeros on a graph, right? If you think back to quadratics, you factor it, you know the 2 points where it will cross the axis. However, when a zero has multiplicity that is more than 1, so a factor repeats itself, then it would have different behavior depending on that multiplicity. So in this case, I notice that there's a lead coefficient that I can ignore for now. We've got this x plus 4, which is just a one-time factor. X plus 1 is happening 3 times, and x minus 3 is happening 2 times. In the graph, I want you to look at the behavior of each of those zeros. Here, we've got the negative 4. Set that equal to 0, you'd subtract 4. Negative 4 is the 0. It passes through like normal. But now, when at negative 1, notice this kind of looks like a cubic function. It levels out and then passes through with opposite end behavior. Whereas x minus 3 squared, the 0 is at positive 3, and it behaves more like a quadratic. It bounces. So when it is squared, it creates a bounce. The multiplicity of a 0, then, is the degree of its factor. We can include multiplicity when we list those zeros. So the solutions, or zeros, for that previous function are x equals negative 4, x equals negative 1 with multiplicity of 3, and x equals 3 with a multiplicity of 2. So at 3, the multiplicity was 2. The graph of the polynomial is tangent to the x-axis, creating this bounce, and the graph of the polynomial will always be tangent to the x-axis at any 0 with even multiplicity. So those even numbers, like 2, create that bounce. For each of the following polynomials, we want to figure out the degree of the polynomial and then find all real zeros and state the multiplicity for each 0. So we're going to go ahead and look at x to the third. So that's like saying x plus 0 to the third. I'm going to ignore the lead coefficient for now. Then the next factor we had was x plus 1. There is no exponent that has a multiplicity of 1. It just happens one time. Then x minus 4 has multiplicity of 2. Now that I have these, we want to find all real zeros and state the multiplicity of the zeros. So x is equal to 0, and I'll put in parentheses multiplicity of, How many times did that x happen? 3. X can also be equal to 1. That's a negative 1, right? Because the sign reverses when I set it equal to 0. And then the last one, x can be equal to positive 4, because I am going to be adding 4 to solve that. That has multiplicity of 2. Go ahead, try B and C. And when you look at this one here, C, I want you to think about whether or not these are factored fully. All right, my hope is that you looked at this and recognized that currently these are not factored. So for the first one, x squared minus 4 should have been x plus 2, x minus 2, and then you still have x minus 2 to the 4th. Now in this case, g of x now has 3 times x plus 2, and then x minus 2 is actually to the 5th power. All right, I can double check by going to my calculator, plugging it into the y equals, clicking graph, and then I'll notice we pass straight through at -2, which is this factor here. So the first 0 is at x is equal to -2. There's no multiplicity there. Then I also know that x can be equal to, and in this case, I notice what type of behavior here. Well, it's an odd degree, so it has a curve, but it does pass through. Remember, odd degrees have opposite end behavior. So here we go. This has a 0 at 2 with multiplicity of 5. All right, now that I've shown you that, gave you a little bit more of a heads up, double check C. See if you've got C figured out. I'll go over it as soon as you press play again. Go ahead, pause for C. All right, everybody, take a look here at C. Notice first I factored out an x, then I took the remaining quadratic, factored that as well. Over here I took the second trinomial here, factored that, and notice that we had a common factor, so that results in a multiplicity of 2 for x equals -3. Then I rewrote them so that I could look at each of the factors and their degrees. X, well, x doesn't have anything added or subtracted, so I know that'll be 0. 2 becomes -2. -3 becomes +3 with multiplicity of 2. -4 is 4. I would love to also notice that if I threw this on a graph, I do have -2 passing through once. I have 0 passing through once. Then the multiplicity at 3 resulted in a bounce off of 3, and then again we cross once at 4. So the one thing about this is if you were to graph it and look at this graph, multiplicity may mean that it has a multiplicity of 2, but remember, all even numbers would have that same bounce, so it could have multiplicity of 4. So you can't necessarily tell directly from this graph right now. I do need you to factor them. That being said, the next thing we're going to talk about are complex roots. So complex roots, they're like confusing trees. Or not. Some polynomials may have imaginary numbers. I hope you remember what an imaginary numbers are. There's an example right here that I'd love to go over. It says x squared plus 1. This is not factorable because you can't get that c value to cancel. The b value to cancel. So instead, you could solve by subtracting 1 on both sides, and you'd end up with x squared equals -1. Then, when you do the square root, you would find out that x is equal to a positive negative square root of -1. And remember, a square root of -1 is imaginary. So, what does that mean for the graph? Well, when you have an imaginary number, it means that you will not see those roots on the graph. So we will not be crossing the axis. Let's go ahead to the next page right here. All imaginary roots come in pairs. If an a plus bi is a root, then that means that a minus bi is a root. That's because imaginary numbers come from the square root. And remember, square roots can always be positive or negative. So the conjugate pairs are just the other version of the imaginary complex number. So if this is 4i, the conjugate would be negative 4i. So b, what would that be? Well, negative I, the other would be I. The conjugate pair for 2 plus negative 3i, 2 minus 3i would be 2 plus 3i. And the last conjugate would be negative 4 minus 2i. So conjugate pairs have to go together. Next, the fundamental theorem of algebra. A polynomial of degree n has exactly n complex zeros when counting multiplicities. So what does this mean? Well, if it's a degree 3, it needs to have 3 zeros. Now, that can include both bounces or multiplicity or imaginary solutions. So let's look at an example here where it says the graph of the polynomial function is shown. We know that x equals I root 3 is a 0. So we know that there's an imaginary solution here. If f has degree of n, then what is the least possible value of n? Let's stop and find the real zeros. So how many real zeros do we know? We know that there is a 0 at x is equal to negative 1. And I also see there's a bounce. That bounce, maybe it's 4. But it also could be 2. So that's why it says the least possible, right? I could say there might be 6 there, but I don't know. So I will stick with the least possible. So I'll say 1 has a multiplicity of 2. Then I also cross again here at 3. So x can be equal to 3. And that one passes straight through, so that's a normal root. Now it's known that x equals I root 3. So would I see that imaginary or complex root here on this graph? No, it doesn't show up in any visible way. But I know that if I have this, then I must also have its conjugate. So I know that there is also going to be a negative I root 3 in here. So I know 2 roots are not visible, 3 happened once, and this 1 happened at least twice. So the minimum number, the lowest degree possible, would be that n has to be greater than or equal to 5. There could be more than 5 zeros, but I know there's at a minimum 5 zeros because the conjugate and its pair, as well as the multiplicity I can see. All right, everyone, we're going to stop there because the second half, we're going to go into inequalities. That will be part 2 of this lesson. So today's work ends here. Bring in these notes, and any questions that you have, we'll get some practice.